page 175, 176. What can I do? What can I do? What can I do? It's pretty easy. Do what? Do we have to what? I think so. So we feel pretty comfortable. Yeah. 8, you got it. Number 8. All right, here we go. Problem number 8. We have create a data display for a data set that is not uniform, not normal, but symmetric. You can make your own data. Okay, so there you go.
How about this? Is this too
That's better.
Really?
Yours is best. First favorite. Hey. Any other questions on 175, 176? Do what? Was one asked? No. We're good? Happy? Content? All right. Sure. Well, you know, I, like you, was got that phone call from Cherry Creek High School last night, or Cherry Creek School District, going, oh yeah, they're calling it. Delayed start. I'm like, come on. So I had to cancel the med class, but it's good stuff. All right, my friends, I am on page 70. This is pretty straightforward, pretty simple. We're finally going to get into, we're getting into what they call the 68, 95, 99, 7 rule. And really all this rule is, we have this normal curve, which is a bell curve. Agree? You have the mean here. And if I go out 1 standard deviation this way, so I add to the mean or I subtract to the mean, this means that inside this data region, we have 34% of the area here, 34% of the area here. So if you wanted to say what is within 1 standard deviation, that would be 68%, because if I go 34 plus 34, I get 68. Then if I go out a 2nd standard deviation, either I add or subtract it. This is going to account for 13.5% of our area under the curve, each one of those little tiny regions. So if I add 13.5, 34, 34, and 13.5 together, I come up with 95%. And then if I go out 1 further standard deviation, so if I add the standard deviation to the mean or I subtract 3 standard deviations from the mean, this little tiny region here is going to represent 2.35%. And this would represent 2.35%. So that means that if I add all of those values all the way up within 3 standard deviations, you're talking about 99.7% of our population. And our very small little n's would account for 0.15%. So once you've gone beyond 3 standard deviations to the left or to the right, you're talking about a small, tiny, itty-bitty percentage. Okay? So this consistent percentage breakdown it's a great tool. If we're talking about heights of people, lifespans of bears, percentages of returns on money, market, mutual funds, cholesterol levels, amount of honey produced by bees, or the humidity level in Seattle, these percentages apply as long as we know that the data set is normally distributed. It does pose some challenges. How do we know that our data set represents normal distribution? Now, I kid you not. Normally, when you're reading a report, they'll say, this is our data, which is normally distributed. So you're supposed to trust the author. Okay? And then, according to the properties of normal distribution, 68% of the observations should lie within one standard deviation of the mean. What if in our data set, 80% of observations lie within one standard deviation of the mean? That would be strong evidence that our data does not represent a normal distribution. In other words, we expect the percentage of our sample region normal distribution to match our 68, 95, 99, 7 rule. So on page 71, they do have some test scores that they had done. We could plug all those in and take a look on the calculator what it would look like as long as we make our rectangles appropriate. But if you did that, you'd be able to find that the mean is 69.8 and the standard deviation is 13.6. So this means this. 69.8 would be our mean. Okay, and they told us our standard deviation is 13.6. So I'd go plus 13.6 to the mean to get one standard deviation this way. I'd subtract 13.6 from the mean to go this way, which would take us to 83.4 or 56.2 as far as values go. And then if I add another 13.6, add it again, that's going to take me to 97. If I subtract another 13.6, that takes me to 42.6. And then if I took it out a third standard deviation, if I add another 13.6, so 3 standard deviation, that takes me to 110.6. If I subtract another 13.6 here, that's going to drop me down to 29. Okay. So according to this rule, 68% of our test scores should lie between a 56 and an 83.4. In actuality, 18 of the 34 scores lie between that gap, which is 60%. That's 8 percentages away. According to the same rule, 95% of our scores should lie between 42 and 97. But if we count up our data, we have 29 of the 30 scores that lie in that gap, which is 97%. So that's 2 percentage points away. According to the same rule, 99.7. So what we're doing is we should have 68% of our data fall here. But if you actually count that up, if we count that up, this only with our data represents 60% with our data. Okay? If I go the second standard deviation out, we should, all the way out here, talk about 95% of our population, but our data actually shows, if we count up the numbers, 29 out of 30, which is 97%. So, friends, can we say this is a normal distribution based on what we know so far? Okay, so think about this. This should be 68% of the data, but it was only 60% of the data. Is it wrong then? Yeah, we can say this is not normally distributed. Okay? So is this good enough for us? We don't know. We can say the data, the set represents a normal distribution, judgment call. However, the percentage point differences is substantial, so it appears unlikely that a normal distribution can describe our data. Okay? In addition, the mean 69.8 and the median is 74. So if we continue to find information, if we found that our median was 74, 74 is, somewhere over here, that means that the mean is being pulled to the left. So this means that we're going to have a skew left distribution. And this is all information you can get from Desmos. Okay? When you go into Desmos and you plot your data, you can, once you go into the statistics, you can find the mean, the median, the standard deviation. It'll do it all for you, just as long as you list everything in X1. Cool? All right, got all the way through my hiccup. So we have 3-3, so 177, 178. For a Monday. Okay. Deal?